Hello everybody, I would like to talk about our investigation on fracture of 3D printed parts. Our research is entitled Effects of Raster Layup and Printing Speed on String of 3D printed components. This research has been performed in the Institute of Product Development at the University of Siegen, Germany. This presentation includes introduction, which covers a classification of manufacturing processes at a glance and an overview of 3D printing methods, their advantages and applications. I will continue by experimental test, where I will describe specimen preparation, mechanical test and results, and finally conclusions. Manufacturing processes are the step through which raw materials are transformed into a final product. The manufacturing process begins with the product design and materials specification from which the product is made. As you can see in this slide, manufacturing process can be classified into three main groups of shaping, joining, and finishing. Each of these groups cover different processes. For example, machining, casting, rolling, and forging can be considered in the group of shaping process. However, new processes have been developed. One of the manufacturing processes which was introduced in the last century is additive manufacturing, and it is known as three-dimensional printing. American Society for Testing and Materials and also International Standard Organization define 3D printing as a process of joining materials to fabricate parts from a 3D model data. They also classify 3D printing into 7 processes, which are binder jetting, material extrusion, direct energy deposition, material jetting, sheet lamination, powder bed fusion, and vat photopolymerization. As can be seen, these processes are suitable for various types of materials such as plastic, metal, ceramics, and glass. Here we present some main advantages of additive manufacturing. Based on the utilized technologies, 3D printing is a fast process which has positive influence on the environment. In different 3D printing processes, multiple materials can be used in one component, which is advantage compared to other manufacturing processes. Based on the documented data, 3D printed parts have excellent quality surface. Moreover, considering printing hollow structures, reduction in material usage is valuable. Regarding to the developments in additive manufacturing, this technique has been used in a wide range of industrial and academic applications. As it is shown in this slide, the 4 main applications of 3D printing is related to the functional models, education, artistic parts, and spare parts. In details, about 15% of its application is belong to the functional models and artistic parts, which are shown by green and yellow color respectively. Moreover, its application in fabrication of spare parts and education and research is equal to 13%. However, additive manufacturing techniques are being significantly utilized in various applications such as mechanical tools and different custom parts. It should be noted that currently AM techniques have been used for prototypes, and also they have been utilized to answer the demands for serial production. Let's go to the second section, which presents details of experimental test. As has been mentioned before, material extrusion is one of the main families of 3D printing process. This method uses continuous filament of thermoplastic or composite material. Fused deposition modeling, or FDM, is a technology in the family of material extrusion. In this technique, the melt extrusion method has been used to deposit filament of thermal plastic according to the specific pattern. In detail, the nozzle moves over the build platform to produce the parts layer by layer directly from a digital model. The simplicity of the FDM process have made this technology widely recognized and used in industry, academia, and research and development sectors. In FDM process, several printing parameters can be changed. For instance, printing speed, nozzle temperature, and printing orientation can be changed. As FDM process deals with several issues, quality and performance of the parts which are produced by this process depends on different factors. Here, a fishbone diagram is presented to show materials and process parameters in FDM printing. For instance, as you can see, raster angle and width, printing speed, and also air gap and layer thickness should be considered as a parameter which have influence in mechanical properties of 3D printed parts. However, it is often difficult to control all of these parameters together. So it is important to investigate and determine effect of these factors on performance of the 3D printed parts. In preparation of the specimens, in this study, a standard was used and the dog bone specimens were printed based on the standard. The specimens dimensions are presented here. Moreover, the relevant details such as air gap, raster, width, and angles are illustrated. Each parameter has own definition. For example, air gap is the distance between two rasters on a single layer of the printed part, or number of contour is a number of solid outer layers that surrounds the internal infill pattern of a printed part. We should note that the value of these parameters have role in the performance of the printed part. In the current study, we used polylactic acid or PLA, which is a thermoplastic polyester, and it has become a common material as it can be produced from renewable resources. Here we consider to change two printing parameters, which are raster angle and printing speed. So let's look to the definition of these parameters. Raster angle is the printing direction relative to the loading direction, and printing speed defined as the distance traveled by the extruder along the bed per unit time while extruding. Therefore, printing time of each part depends on printing speed. Here you can see the dog bone specimens which are produced with different raster angles. It should be noted that these specimens are fabricated under two printing speeds. As you can see in the figure in the left side, the angle alpha is the printing direction relative to the loading direction. Based on the angle alpha, sample with 0 degree refer to the specimen which experienced loading in the raster direction, and sample with the 90 degree refer to the specimen that are loaded perpendicular to the raster direction. This table presents details of raster orientations. Also, it shows that the specimens are printed with the speed of 20 mm per second and 80 mm per second. It should be noted that we printed all the specimens with the infill of 100% and all other print parameters were kept constant for all the specimens. In this slide, we present details of sample printing. As you can see, all the specimens with different raster orientations are produced in 8 layers. Also, the table shows printing parameters such as nozzle temperature, bed temperature, layer thickness, density, and number of contours. Let's go to the details of mechanical test. In this study, we have conducted a series of tensile tests on 3D printed PLA specimen, and to this aim we use a hydraulic machine with 15 kN load cell. In this figure, you can see a 3D printed specimen under tensile test condition, and The tests have been performed with the tensile speed of 0.1 millimeter per second until the failure. All the tests are conducted at the room temperature, and it should be noted that the tests were repeated 6 times for each raster orientation and printing speed. Here we present results of our research. First of all, we show the fractured specimens. For the specimen with the raster direction of 0 and 90 degree, the crack is perpendicular to the loading direction. As can be seen in the other specimen, the cracks are oriented with the raster direction. Moreover, we have observed brittle fracture in all the examined specimens. As the second result, here we present different curves obtained from the experiments. The graph in the left side is stress-strain curves of the specimen with different raster orientation, which are printed with the speed of 20 millimeter per second. As can be seen, the highest stress belongs to the specimen with raster orientation of 0 degree. Also, the curves show that the lowest stress is related to the specimen with the raster direction of 90 degree. The curves in the right side are related to the specimen which are fabricated with printing speed of 80 millimeter per second. Similarly, the specimen with the 0 and 90 degree raster direction showed the highest and lowest stress respectively. In both cases, I mean the printed specimen with 20 millimeter per second and 80 millimeter per second, the stress value is decreased while the raster angle is increased. Based on the experiment, we report that brittle fracture for all groups of the specimen, as we have seen sudden failure after reaching the maximum stress. It should be noted that our investigation show sudden failure, which is result of fiber debonding through all layers. Therefore, alternating layup can prevent this type of failure, which will lead to additional resilience and increase the elongation. As another part of the result, here we present curves to show dependency of elastic modulus and tensile strength to the raster direction. The graph in the left side shows elastic modulus versus raster direction, which is alpha in degree. As can be seen, the Young modulus is decreased with increase in the raster direction. Therefore, the highest elastic modulus was obtained from the specimen with alpha equal to 0 degree. Moreover, the curves in the right side show dependency of tensile strength on the raster direction. The obtained result confirmed that the specimen with the alpha equal to 0 and 90 degrees showed the highest and lowest tensile strength respectively. Indeed, the experiment indicated that there is a gradual decrease in the tensile strength with increase in the raster direction. In the last part of the result, we show these figures which are obtained from the visual inspection. In the current study, all the specimens are visually investigated by a free angle observation system. Visual investigation showed that there is no plastic deformation, and also this microscopic investigation showed gradual damage in the raster. In fact, the rasters which are not parallel or perpendicular to the load direction undergo a rotation and reorienting into the loading direction. As you can see in the figures, cracks are oriented with the raster direction. Please let me to conclude this presentation. Currently, additive manufacturing techniques have been used for prototype and also serial production. So this issue indicates necessity of further research in this field. In this presentation, I have described advantages and application of 3D printing technology. Later, I have explained details of 3D printed specimen and also series of tensile tests. Based on the experiment, we have obtained stress-strain curves, and from these curves, we can directly see both strength and stiffness. depend on the raster orientation and printing speed. Particularly, it can be seen that the specimen with raster orientation of 0 degree have highest strength and stiffness. The obtained results showed that both parameters are decreased with increase in the raster angles. Moreover, we have performed fractography analysis and the obtained results are presented. This work, as a part of the project the Smart Production Design Center, is funded by the European Regional Development Fund. Thank you for your kind attention.